So you can describe the composition of a solution, all the components involved, by expressing their concentrations, their individual concentrations. So you can actually talk about concentrations both qualitatively and quantitatively. For example, qualitatively, you could just say, oh, that solution is just a dilute solution, or that solution is a concentrated solution with, relatively large amounts of solutes or relatively small amount of solute. But oftentimes in real life scenarios, that information is inadequate, or sometimes can be confusing, and you really need to talk about numbers or talk about quantitative descriptions when, to make informed decisions. So for example, let's say somebody just hands over a solution of cleaning liquid and says, it's just a dilute acid and don't worry about it even if it falls on your skin. Then you're not going to buy that, because that is clearly a safety hazard, and you really exactly need to know what the concentration of the acid in that liquid is, and what are the safe limits for your skin, and what are the safe limits for the surfaces that you're cleaning it with, and things like that. And only then you'll be able to make an informed decision, regarding whether that particular cleaning liquid is right for you or not. So that is just a very simple example, but you'll come across a lot of situations in our day-to-day lives where you'll appreciate the need to actually quantitatively express the concentration of components in a variety of solutions. So in any case, so let's look at what are the different ways of expressing concentration of solutions quantitatively. So one simple way of talking about concentrations would be mass percentage, which is basically any given component in the solution. You can talk about a mass percentage, which is mass of the component in the solution divided by mass of the solution times 100. So for example, if you have table salt dissolved in water and you say it is 10% by mass, then what it means is in every 100 grams of solution, you have about 10 grams of sodium chloride and then 90 grams of water. So this is 10% by mass concentration. So generally, this way of expressing concentrations is used in, industrial chemical applications, and it comes very handy when you have a solid solute dissolved in a solution, where it's easier to measure the mass of the solute than the volume of the solute. So similarly, you can talk about a volume percentage, where you have the volume of the component in the solution divided by total volume of the solution times 100. So very similar to the mass percentage, but it's just in volumes here instead. So this comes very handy if you can imagine when you have, liquid solutions where the solute is liquid and the solvent is a liquid as well. For example, if you're talking about an alcoholic beverage and you say it is 10% alcohol in it, and so what it means is every 100 milliliters of that beverage, you have about 10 milliliters of ethanol, and the rest is water and other components. So you get the idea. So we had mass over mass and volume over volume. You can also have mass over volume percentage, which is basically mass of solute, that particular solute present in every 100 milliliters of the solution. So next, another sort of really important way of representing concentrations is parts per million. So this particular unit, ppm, comes really handy when you have solutes in trace amounts in a solution. So very, very tiny amount of solute. So in cases like, for example, people in environmental sciences use this unit quite a lot, because if they're describing, let's say, the concentration of toxins that are present in our drinking water or present in the air that we breathe, or the soil that we live on. So in those situations, you often use this unit. And so it's really important for the environmentalists to actually track these toxins or contaminants, because they can get really dangerous very soon. So we talked about in an earlier video, we talked about how fluoride ion concentrations in our drinking water can be really dangerous if they go beyond 1 ppm to our teeth and to our health in general. So it's really important for us to track the concentrations of these ions. So what it is the number of parts of that particular solute divided by the total number of parts and of all components in the solution times 10 to the power 6. And when you say parts, it can either be by mass or by volume. So you can have, let's say, 1 ppm of a certain component can be 1 milligram of a solute in 1 kg of solution. So that is 1 ppm. That can be 1 ppm. Or it can be 1 microliter of a solute in 1 liter of solution. So you could actually write this as 0.000001 liters in 1 liter, or you can say, or 0.001 milliliters in 1 liter of solution. So basically, this unit is really convenient and handy because you can avoid all these zeros next to the decimal, and you can instead just say, oh, the concentration of that particular component is just 1 ppm. So that saves us a lot of hassle in cases where the solute is present in very tiny amounts. So people even talk about ppb as a unit, which is parts per billion. So this is where even ppm is too large a unit for measuring the concentration of solute. So this is even smaller amounts of solute. Sometimes you see that people refer to ppm as being milligrams per liter, and that often happens when the solvent is water, and it can get very confusing because it's not always right to equate 1 ppm to 1 mg per liter. It might be true in cases where the solvent is water. The reason for that being, at room temperature, close to room temperature and 1 atmospheric pressure, 1 liter of water measures very close to 1 kg. So you have to be really careful when you actually express ppm in terms of mass by volume.